Hello there guys, welcome to my channel. Okay, in this video I'm going to explain to you about physics paper 4 43 May-June 2021. Okay, the time duration here is 1 hour and 15 minutes. Okay, let us move on with the first question. Okay, first question. Figure 1.1 shows a load suspended from a spring. Okay, this is spring, this is the load. Okay, value of the spring constant K of the spring is 0.2 Newton per centimeter. The spring reaches its limit of proportionality when the load is 15 Newton. Okay, calculate the extension of the spring when the load is 3 Newton. Okay, let me scroll down. Okay, the mark is 2 marks here for this question. Okay, so the formula that you have to use for this question is F equals to Kx. The K is a spring constant and the X here is the extension. Okay, so now the load is 3 Newton. K is given 0.2 and the X is the extension. So we just have to divide this and you'll be getting your answer as a 15 centimeter. Okay, how I get the centimeter is because of this. Alright, so this is a 2 marks here. Okay, let us move on with the next one. Okay, the next one is explain what is the mean by the term limit of proportionality of the spring. Okay guys, so this is my answer here. Okay, up to the limit of proportionality of the spring, extension is directly proportional to the load without having damages to the original length of the spring. So if you notice, there are certain spring, if you are stretched beyond its limit, you will have the permanent damages on the spring. Okay, so this is 2 marks. And then let us look at the next one. Okay, C. On figure 1.2, sketch an extension load graph of a spring. Label the limit of proportionality with the letter L on your graph. So this is the extension axis and load axis. Okay, for the graph here, first you have to draw a straight line starting with a 0. From here, a straight line. Okay, a straight line. And then you have to draw slightly above. Okay, so this is the permanent damages. So you can draw a straight line. Okay, and you can point this point as your limit of proportionality. Okay, so here is the where the spring breaks. Okay, guys, so for D, the load is pulled down a small distance below its equilibrium position to position A. So your equilibrium position should be around here. Okay, as shown in figure 1.3. The load then moves up and down between position A and position B. So the equilibrium position should be somewhere between A to B. Okay, so this is the original position. So this is the equilibrium position. Okay, so now the question here is describe the energy transfer which occur as the load moves. Okay, from position A to equilibrium position, which means the position A to here. Okay, this equilibrium position, and they're asking the below here. Okay, from equilibrium position to position B. So from here to here. So what is the energy transfer that happens over here? Okay, the first one here is due to the elastic energy of the spring. Okay, so from the position A to equilibrium, okay, so it is the elastic energy of the spring. It is moving. So once it is started to move, you will have the kinetic energy there. Alright, so this is for from A to equilibrium. So first part is done. The second part, if you look at it, the load is still moving. So if it's still moving, it has kinetic energy. Then later on it will be converted to gravitational potential energy due to its highest position. Alright. Okay, so this is the answer, and the marks here is 3 marks and total 9 marks for the first question. Okay, for the second question, figure 2.1 shows a bookshelf with two groups of book A and B on it. Okay, there are 6 books in each group of books. All books are identical. The mass of each book is 0.52 kg. Okay, this is group A and this is group B. Okay, now the first one, explain why the pressure exerted on the shelf by the books in group B is less than pressure exerted on the shelf by the books in group A. So if you look at the pressure's first formula is given by pressure equals to force over area. So now if you're talking about the force, okay, it is coming from the weight force, which is the weight equals to mg. And since all books are identical, each has 6 books, so they will have the same force. Alright, they will have the same force. The only thing that makes difference here is the area. So if you look at the group A, their area is slightly smaller compared to group B. So when for the group A, the force is constant and the A here is minimum. So once it is minimum, the pressure that is exerted at here, this area here, is much more higher. Okay, here you will have a maximum pressure. However, if you look at here, the area here is larger. Okay, you have a large area compared to your group A. So when you're using the formula F over A, when you have a large area, the overall calculation, the value of the pressure will reduce. So here you will have a minimum pressure. Okay, so this is the explanation for this. So let us answer this question. Okay, explain why pressure exerted in B is lesser than A is because the area, you can explain in such a way that area in group B is larger than area in group A. And you can add on here, since please look at the marks, right? Okay, since you can say pressure is inversely proportional. Okay, so pressure is inversely proportional with the area. So you can say that large pressure, large area resulting in minimum pressure, or you can say a small amount of pressure. Okay, so this is the explanation for this question. Okay, now if you look at the second question, calculate the pressure exerted on the shelf by the books in group A. So we follow the formula, and the force here will be mg. It follows the weight formula. Okay, so here we will have a calculation of 0. So how much is here? This is 0.52. Okay, 0.52. 0.52 times with 6 and then times with 10. 10 is from the G. So based on my calculation here, so you'll be getting 3.12, the total mass, okay, multiply with 10, and here you got 31.2. So here's about 31.2 Newton. Now let us calculate the area in group A. So area in group A is given by, okay, so we have here 21 centimeter, okay, 21 centimeter, which is 0.21 meter, and here is 1.3 centimeter for each book, the width, and here we have about 6 books. So 1.3 times with 6 times with 6, you'll be getting here about 7.8 centimeter. Change it to meter form and you'll be getting 0.078 meter. Okay, so here, will be 0.078 meter multiply with 0.21 meter. So your total answer here will be 1904.7 Pascal. Okay, so I hope you understand this. Okay, now the next question. A diver dives to a depth below the surface of the sea where the total pressure is this. The atmospheric pressure is already given here. The density of the seawater is 1030. Calculate the depth of the diver below the surface of the sea. Okay, so now we have a total pressure here, which is 3.0 multiplied 10 to the power of 5 Pascal, and you have to minus with the atmospheric pressure, okay, which will give you about 2.0 times 10 to the power of 5 Pascal. Okay, this is pressure under the liquid. Pressure under liquid. Okay, so the pressure under the liquid, you have to use this formula, H, rho and G. Okay, so here the depth will be the H, so we can ignore the H, and the density of the seawater is 1030. Multiply with G, which is 10, and we just have to divide this. Okay, we take the value. Divided by this one. So total you'll be getting there here about 10,300. So this calculation will give you about 19.4. Okay, 19.42 meter. This is your answer. So I hope you can understand this one, guys. So the total mark for the second question is also 9 marks. Okay, for the number 3, a car travels at constant speed v on a horizontal straight road. The driver sees an obstacle on the road ahead. So A, the distance traveled in time between the driver seeing the obstruction and applying the brakes is the thinking distance, or sometimes this is also called as a reaction time. Okay, reaction time. In some questions, they will refer this situation as a reaction time. Okay, now explain why the thinking distance is directly proportional to the speed. Okay, now let us go back to some basics. So what is the speed's formula? Speed is equals to distance over the time. Alright, so now they are asking why the distance, thinking distance, is directly proportional to v. Okay, now the car here, okay, you can see the car and there is an obstacle here, and okay, they are moving in a constant speed. Alright, they are moving in a constant speed v. There is no changes in the speed here. Okay, so from here to here, once the driver notices there is an obstacle, he will take about 5 to 10 seconds. So maybe this is the reaction time. Okay, so this is the reaction time, or we can say as a thinking distance. Alright, so in this particular part. So here, if the distance, thinking distance, and the speed is directly proportional, it means that the thinking time is constant. Okay, the reaction time is constant. This is your answer. Okay, now let us look at B. When the brakes applied, the car decelerates uniformly to rest. The frictional force applied by the brakes is constant. The distance traveled between first applying the brakes and the car stopping is the braking distance. So which means this is the thinking distance, number 1. Alright, so the number 2 here is what we call it as a braking distance, the number 2. Now explain why the braking distance is proportional to v square. So once you look at the v square here, we are getting a point that we can use the kinetic energy. Okay, so the kinetic energy is given by the formula 1 over 2 mv square. Alright, so at the same time here we can also use work done. Work done is force times with the distance. So force here we are referring to the frictional force. Okay, the frictional force. So we can conclude that we will have this formula Fd, the work done, okay, equals to the kinetic energy. Work done equals to the kinetic energy. So 1 over 2 mv square. Oh, I can change this to mv square over 2. Okay, mv square over 2. So explain why braking distance, which is the d, okay, braking distance, the d, and is directly proportional with the v square. So now you can see the point here. So the distance is directly proportional with the v square. So in your explanation, here will be 1 mark, and here you have to write the work done equals to the kinetic energy. Okay, so this one will be the second mark, and the last one is this. This is your 3 marks. So in your explanation, you have to include all of this. Okay, now let us move on with the next one. Okay, the car is traveling at 22 meter per second. This is the speed. Okay, speed I put here V. The thinking distance is 15 meter. Calculate the time taken to travel the thinking distance. So we can use the formula. The speed equals to the distance over the time. So now by using this formula, so we have the value 22, 15 over the time. So we flip the time and 22. So we have 15 over 22, which will give you 0.68 seconds. Okay, so this is your answer. Okay, now look at the next one. The car has a mass of 1400. The time taken for the car to stop after the brakes are applied is 2.1 seconds. So calculate the force required to stop the car in this time. So here, so this is a sub question, okay? So you can always refer to the main one, which is the speed is 22. So we can use the formula of impulse force. So we can factorize the mass. Okay, so we can substitute the values here. The force will be, what's your mass? Mass is 1400. And your final velocity here will be 0 minus with the initial velocity, which is 22, divided by the time 2.1 seconds. So the calculation here will be 1400 multiplied with 22 divided by 2.1. So here I'm getting about 14,666.67 Newton. Okay, so this is your answer here. If you want to add in the negative sign, you can add in. The negative sign, it shows the force will be impacting the brakes. Okay, impacting the brakes. So this is your answer here. It's 2 marks. Okay, for number 4, define a specific latent heat of fusion. Okay, this fusion is solid to liquid and liquid to solid. Okay, it's a change of a state of matter without changing the temperature. So your definition here will be, so the answer that I've suggested here is the energy transferred when 1 kg of substance freezes or melts, okay, like solid to liquid or liquid to solid, with no change in temperature. Alright, so this is the answer for this question. Okay, the next one here. A cup of water contains 250 centimeter cube of water at a temperature of 0 degrees Celsius. An identical cup contains 250 centimeter cube of a mixture of ice and water at a temperature of 0 degrees. The temperature of the surrounding air is about 20 degrees Celsius. Okay, now state and explain which cup contains the liquid with the lower temperature after 10 minutes. Okay, this is the statement and this is the explanation. So your explanation here will be the cup containing mixture of ice and water. Okay, so why? Because the temperature of the mixture of the ice remains 0 until all the ice melts. So if you look at the first statement here, it only contains water. So water, it doesn't has any ice. So what happens is the temperature of the water will rise until it reaches equilibrium with the surrounding air temperature. Right? Okay, let us move on with B. Okay, here B1, on a hot day, sweat forms on a person's skin and then evaporates. Explain in terms of molecules how the evaporation of the sweat cools the person. Okay guys, so this is my explanation here. So layers of sweat molecules absorbed heat from the skin. Okay, example like this, the picture 1 and it's the picture 2 and picture 3. So as you can see, the red molecules, okay, the molecules at the red layer here will be absorbing the heat from the skin and then they evaporate and leaving behind the green color layer, and they will continue the same process and then they evaporate. Then you have the last molecule, okay, the last layer of the liquid, the blue color, and they'll continue the process. So this continuous absorbing of the heat from the person is cool off the person. Alright, so here for 3 marks you have to maintain the first point. Second point is molecules obtain more kinetic energy and evaporates, leaving the remaining liquid on the skin. Okay, so this heat loss cools off the person. So this is the answer for this question. Okay, now explain why this process is more effective when a wind is blowing. Because you could say that it's a moving air increase the rate of evaporation. Okay, so this is your answers guys. This is 8 marks for this question, the entire question. Okay, now let us move on with the question number 5. Okay, question number 5, a figure 5.1. Okay, this is a 5.1. Okay, let me make it slightly lower. Okay, this is 5.1. Shows a wave on a sea approaching a harbour. Okay, this is the harbour wall and this is the gap. Okay, now let us look at the question here. Okay, the question on figure 5.1, draw 3 wave crests in the harbour. So we need to have a comparison. All right. So okay, now let us go through the next question. Okay, another harbour has a much wider gap between its wall. Okay, this process is called as a diffraction process. Okay, diffraction process, and they are influenced by a 2 factor. One is the size of the lambda. Okay, this is the lambda here, the wavelength, and they also, you have another factor which is the size of the gap. Okay, size of the gap or opening. So these are the 2 factors that influence the diffraction effect. Okay, another harbour has a much wider gap, which means this is a smaller. So if it is a smaller gap, the smaller the gap is, the wider its effect. So here you just have to draw a circular shape. Okay, circular shape. So this is the 3 wave crest. So this is your answer for the first one. Okay, now when they mention that much wider gap between its wall. Describe and explain how the pattern of the wave crest in this Haber is different from the pattern you have drawn in the first one. And this is a description and this is an explanation. Okay, let me draw the wave. Okay, let me draw the wave by using another color. The red one is for the first, the answer for the first one. Okay, and the green one, it should be like this. A straight line. Okay, it's a straight line. This is the answer for the second one. Okay. So the pattern here, your description here will be wave pattern remains in straight line. And your explanation here is because you can say no diffraction occurs. So this is your answer for this question. Alright. So please remember this. Okay, now we are going to the next question. Okay, for B, a sound wave of frequency 850 Hz travel through seawater. The speed of sound in seawater is 1,500 meter per second. Calculate the wavelength. So we just have to use this wave formula. The speed is 1,500. The frequency is 850, and this is the lambda, the wavelength. So what we have to do, we just have to do a division here. Okay, now the value you can calculate. You'll be getting 1.76. Okay, 1.765 meter. So this is your answer for this question. Okay, now we move on with the next one, number 6. Okay, number 6, figure 6.1 is a full-scale diagram of a lens and an object O. So the focal length of the lens is 3.5 centimeter. On figure 6.1, mark and label with letter F the position of the two principal focus. Okay, now just get your ruler. So it is a 3.5 centimeter, right? So make sure the distance must be measured from here, okay, from the center of this lens. Okay, let me make it bigger. Alright, okay. So this is the center. So it's 3.5. Should be exactly at here. Okay. So now you just have to mark here, exactly here. This is your principal focus. So I just put here F. And another side here, 3.5. So 1, 2, 3. So exactly over here. Okay, let me remove the ruler. So we just have to put here F and F. So this is the principal focus for this lens. Alright. So okay. Okay, so we have marked and labeled the letter F, okay, at these two principal focus. Maybe I'll make it more accurate. Okay, now for B, on figure 6.1, draw 3 rays to locate the image. Draw an arrow to represent the image and label the image I. Okay, the first step here is we have to draw a straight line. So I'll be using different colors. Okay, from here, straight, okay, straight to the center of the lens. Then from here you have to go through the focus point. Okay, this is ray number 1. Okay, ray number 1. So this is the arrow. Okay, then you have to draw the second line, which is exactly passing through the center. Okay, the center. Okay, this is number 3. This is ray number 3. Sorry, ray number 2. And okay, for the number 1, I have to extend the line so that it meets okay, I have to erase this part. It's a small modification here. And drawing the green. So make sure it is a straight line. And you can see this the intersection point here, right? Okay, so this is your image. So now I have to draw another line, which is, let me use red color. Okay, this is the line, straight to the left. Okay, after you have drawn the first one, so make sure you draw a straight line, okay, toward this. So okay, now let me draw the arrow. So this is the arrow. This is your third ray. So the first one is the green color. The second one is the blue color line. It will passing through the center of the optic. And this is the third line. Alright. So this is your image formation. This way, okay. You can see the point where all the rays are intercepting here, right? Okay, so this is the intersection. Intersection is of all the rays. So over here, you are going to draw the image straight and draw this. Okay, this is the image. Okay, this is the image. It's quite hard to draw in this software. So if you can print out this paper and you can draw it using your ruler and your pencil, it will be much accurate compared to mine. Alright, okay, so make sure you just follow this. Okay, then they are asking the C, state the 3 properties of the image 1. So if for the lens, the object is here and the image at the opposite side, then it is a real. And this is a inverted. Okay, inverted. And you can see the size is much more bigger, right? So you can say it's also magnified. Okay, the image has been magnified. So here's 2 marks for you. Okay, now Move on with the next one. Okay, a student incorrectly states that this lens is being used as a magnifying glass. So to have a magnifying glass, alright, so what you have to do here is the image, the object has to be placed below the less than the distance of the principal focus, which means the object must be less than the distance over here. So let us look at the question. Okay, state how the image produced by magnifying glass is different from image 1. So let me explain to you about the magnifying glass. Okay, I just give you a basic drawing. Okay, now this is the lens. Okay, this is the lens. You can ignore the drawing. Okay, so let's say I just put an example of this is the focus, principal focus, and the image is here. Alright, so I'm going to use the first one, which is going straight and going down. Okay, so this is the first ray number 1, and look at ray number 3. I'll be using the second method. I'll be passing through the center of the optic, and if you compare both of these, they are not going to intersect, but they are going to intersect at over here. So I'm going to draw the line which is beyond, okay, here, and for the black color, line is here. So this is the image that forms. This is the image that forms. So this is how the magnifying glass, okay, this is the image. So this is the shape of the magnifying glass drawing. Okay, magnifying glass. And the image here is virtual because the object and the image is at the same side. Okay, so here state how the image produced by magnifying glass is different from image 1. So you can say the image is virtual. Okay, the next one. The student moves the object O to position P so that the lens shown in figure 6.1 acts as a magnifying glass. So mark the possible position of P. So what you can do here at this part, the position P you can label somewhere within this space, as I explained just now. So you can put here, okay, here as P, or here as P, or here as P, as long as it is lesser than the focus point. Okay, so this answers the question. So I hope you understand. So I have a specific video only for this lens drawing, which I will share the link in the comment, or you can check out my channel. Alright, okay, so let us move on with the next question here. Okay, now the next one, number 7, define electromotive force. Okay, this is normally the force from the battery. Okay, so I will write here my explanation. Okay, so this is the explanation for this. Energy supplied to drive a unit charge 1 coulomb, okay, in a circuit. You can also change the energy supply to work done, which is derived from this formula. This is the voltage formula. So we have a work done over the charge. So this is a joule and this is a coulomb. Okay, so you have this unit. So you can remember this formula, or you can memorize this. Okay, now for figure 7.1 shows a circuit. Okay, here is 12 voltage, PQ, and there is a 2 bulb. Okay, let me try to make it bigger. No. Okay, the two lamps shown are identical, so they have the same. Each lamp has a potential difference of 3 voltage across and a current of 2 meter in it. PQ is the length of a uniform metal wire. So resistance of PQ is R. Okay, so the calculation here will be it's quite simple because in parallel. Okay, if you look at parallel, this is a parallel connection, right? This is a parallel connection. So I just put here the V, the voltage. So the voltage at in the parallel circuit must be the same. So here is about 3 voltage. So here will be 3 voltage. Okay, 3 voltage for both. If here is 3 voltage, the PQ and the bulb is series. So here will be the balance. So 12 minus with 3, you'll be getting here about 9 voltage. Okay, and look at the current. Now voltage done. Now look at the current. So they mentioned that a current of a 2 ampere in it. So here we have 2 ampere and here we have 2 ampere. So in the parallel circuit, the current will be divided. So when they combine, here will become 4. Okay, here will become 4. So 2 plus 2, you'll be getting 4. So which means the current over here is about 4 ampere. Now we can definitely find the value of R. So we just use a V equals to IR. The V is 9. The resistance of the current is 4. Resistance is R. So we just have to divide this. So the R value we are getting here is 9 divided by 4. So you'll be getting here 2.25 ohm. Alright, this is a 2.25 ohm. So which this is a 3 marks. And then another piece of wire is made of the same metal, PQ, and the length of the new piece of wire is twice the length. Okay, let's say the resistance, we have a formula of, okay, this is the resistivity, length, and also the area, surface area. Okay, surface area of a wire is given by the area of a sphere or of a circle. So it is a pi r square. So if you want to derive this, look at here. Okay, they mentioned that the diameter of the new piece of wire is twice the diameter of PQ. So we just label the original diameter as D. Okay, so which gives D over 2. Okay, D over 2 square. Then we will have D square over 4. So this is the area. So let us get the original. So this is P, L, and here will be pi D square over 4. So the over 4 will be inverted, and here this is the original. Okay, this is the original PQ. Okay, now we have to modify this. We are going to use the same one. So the length is 2 times. Okay, length is 2 times, and the diameter of a new piece of wire is twice. So which means 2D over 2. Okay, so now here will be pi 4. You can actually simplify this. Okay, simplify this thing, and you'll be getting pi d square only. So here is pi d square. So this is the new one. Yeah, so I just put here n, and here will be 2 pl over pi d square. Okay, so this is the new resistance. The new resistance. So I just put there Rn. So this is how you derive from these formulas. So this is new, and this is the original one. So the original one is valued at 2.25. Okay, this is a 2.25 ohm. So here will be halved, right? You can see the 4 and the 2 here. So here we have to divide 2.25 divided by 2. So you'll be getting here about 1.1. You'll be getting 1.13 ohm. Okay, so this is the answer for this question. Okay, so now I hope you can understand this. This is for number 7. So let us move to question number 8. Okay, for number 8a, state the difference between an analog system and also a digital system. You may draw a diagram to help explain your answer. The same question, it came out in 2020. I'm not sure which papers, 4.3 or 4.2. Okay, so for analog signal is a continuous signal. Okay, it's a continuous signal. They are a moving database. Okay, it's a moving database. However, this digital signal here, you will have the numbering. Okay, the numbering like 1. If you look at the binaries, you have 1 0 0 1 1 0 1. So example 0, you don't have any data. 1 you have here, and 0 and 1 again. So this is a digital signal. So this is more to discrete, and this one is a continuous signal. Okay, so these are the main difference for both of these. Okay, this is my rough explanation here. So this is analog, has a variable signal with any value, so it's a continuous. Okay, and a digital signal here, it has only two, which high means is 1, and low, which is 0, output only. All right, so this is for number 8a. Okay, now let us go to B. Draw a symbol for a NOR gate. So NOR gate is actually a combination of an OR gate plus with a NOT gate. So they have a shape like this. This is OR. Okay, this is OR, and they will combine with the NOT gate. This is NOT gate. So when they are combined, you will produce NOR. So it is just like a OR gate, but you have a circle here in front. So this is a NOR gate. Okay. Okay, for C, 8.1 shows a combination of logic gate X, Y, Z. The gate are not represented by standard symbols. So here table 8.1 shows a partly completed truth table for this combination of logic gates. Okay, so now what is the question? So from table 8.1, deduce what's the name of logic gate X and Y. Okay, now let us look at this. So we just focus on logic gate A, B and D. Okay, A, B and D. So if you look at this one and the D here, they have a pattern of a AND gate. Okay, they have a pattern of a AND gate. So this is the AND gate. Now look at D, C and E. So let me erase this. Now we are going to D, C and E. D and C is the input. So D and C. Okay. So this is the C and D as the input and E as the output. So you can see here, this is 0. It looks like it is the OR gate. So OR gate, they have a 0 0 0 1 1 0 1 1. So the output of an OR gate is either if either one of the input is 1, here you'll be getting the output 1. Okay, this is the actual OR gate. And if you look at here, the E side, and there's no 1. So most possible answer, the logic gate for Y is OR gate, which is this. And OR gate is being divided its signal to 2, and that is the logic gate Z. So we just have to write it down here at this part. This is AND gate and this is an OR gate for Y. Okay, logic gate Z is a NAND gate. NAND is AND gate with a NOT gate. Okay, so they have a symbol like this. This is a AND gate and this is a NOT gate. So combination of this circuit, they have this. Okay, now let us deduce the truth table for this. So their truth table here will be, let me do it up here, so it's much more convenient. So let's say this is input 1 and input 2, and this is the output for NAND gate. We try to do it for AND gate first. Okay, AND gate. So we have 0 0 0 1. Here should be 1 0, and here's 1 1. So if it is an AND gate, it should be 0 0 0 1. All right. So here is a NAND gate, which is 1 1 1 0. So this is the answer for NAND gate. So we just have to make it opposite. So here we have 0 and here will be 1. Here's 1. Here's 1 1, and the 0 will be the opposite. From here will be 0. Okay, 0 0. So this is your answer for this. There's 7 marks in total. Okay, now let us move to the next question. Okay, for question 9a, an X-ray machine required a supply of 110 kilo voltage. This is quite high. The main electric supply is 230 voltage. A transformer is used to supply the correct voltage to the X-ray machine. There are 50 turns on the primary coil of the transformer. So they asked to calculate the number of turns on the secondary coil. So what we can do, we can use this formula. Okay, we can use this formula, or I can change it to Vs. This one is Ns. N is referring to the number of turns, and V is the voltage. So here we have 110 times 10 to the power 6. Here we just have to substitute this. This is required, so 110 is a kilo, right? So 123 divided by 230, and the primary coil is about 50, and we just have to calculate the secondary coil. So 50 will move here, it will become multiplied 50 divided by 2300 equals to an S. So secondary coil. So when you calculate this value, you will be getting you'll be getting 23,913. Okay, so we need this much of number of turns in order for us to get this much of voltage. Okay, draw a second one. Draw a labeled diagram of a step down transformer. On the label, state a suitable material for each of the component. So to draw a transformer, you just need to draw a square. Okay, just draw a square and another smaller square in the middle, and this is step down, so make sure you have more coil in your primary and less coil in your secondary. So the wires are made from a copper wire, and this is a soft iron core. Okay, this is a soft iron core. Step down. Okay, state a suitable material for each of the component. So this is the rough drawing. Okay, so you'll be getting here 3 marks. Okay, now let us move on with this one. Explain how a transformer operates. Okay, so the marks given here is the 3 marks. So for your understanding, the transformer only operates in a AC current. It doesn't operate in a DC current. All right. So I will write down here step by step how does it operates. Okay. So this is my explanation here. When a current flows in the primary coil, okay, when it flows in the primary coil, it generates changing magnetic field because it is a AC. We can add on here the AC current, okay, because AC you have a changing magnetic field which is positive, negative, positive, negative. So it always change. So you'll be having a changing magnetic field which will be transmitted. So the magnetic field will be transmitted to the entire core of the transformer. And here, what happened here is the magnetic field will be cut in the secondary coil. So the secondary coil will be cutting the magnetic fields as it is changing. Okay, and is able to generate the current at the output. Okay, so this is your answer for this question. Okay, for number 10, figure 10.1 shows a beam of radiation in a vacuum. A beam contains alpha, beta and gamma rays. Okay, this is the beam. You have alpha, beta and gamma. Okay, region of uniform magnetic field out of the page. Okay, the beam enters a region where there is a strong uniform magnetic field. The direction of the magnetic field is out of the page. So on figure 10.1, mark and label the path through the magnetic field of alpha, beta and gamma. Okay, for this question, they did not give us the polarity of this magnetic field. So we have to draw the alpha and beta in the opposite side. Okay, it's either if alpha is down, beta can go up. So we start with alpha. So the alpha will be straight line and going in this direction. Okay, so this is alpha. Alpha is 4,2 helium. However, the beta, let me draw in a different color for beta. Beta is a 0, -1 electron. It is much more lighter. So okay, so it will go through the straight line and it will bend. Okay, so they have a much more greater deflection compared to beta because it is light. This one, it has a high inertia. Okay, it has a high inertia. Okay, now if you're talking about gamma, gamma will be going on in a straight line because it is not deflected. This is gamma. Okay. Okay, now label, mark and label. Okay, this is done. Okay, now the last one is the radioactive source have many uses in medicine. State 2 safety precaution which hospital staff take when working with the X-ray source. So one you can say is a limit the time. Okay, limit the exposure time. And secondly, you can say always store the radioactive source in lead box. Okay, so these are the two precautions. Okay, see, the radioactive isotope iodine 131 is used as a tracer in a medical diagnosis. A nucleus of iodine 131 contains 53 proton and 78 neutron. A symbol for iodine is I. So use the nuclide notation to show this isotope of iodine. So here will be the proton number. Okay, down here will be the proton number. So we write here 53, and this one is 53 plus with 78, which will give you 131. So we just have to write it in this way. So this is your answer. Okay, 1 mark. Okay, then the next one, iodine 131 emits gamma radiation. It has a half-life of 8 hours. Explain why this emission and this half-life makes iodine 131 a suitable material for the tracer in a medical diagnosis. Okay, so there is 2 points over here. Gamma has a weak ionizing power, so it can produce a little effect in our body. And gamma ray has a high penetrating power, so it can be detected outside of the human body. And you can also add on, it has a low half-life. Okay, it has a low half-life which can produce a little effect in our body. So you can add on these points as an additional. Okay, so this is the answer suggestion for this question. So I hope so this is the last question, and I hope you can understand and you can learn something from my video here. So thank you for watching, guys, and please like and please subscribe. All right, thank you very much. All the best for your exams.